Welcome listeners to the second part of our discussion on engineering geology, and like we have been discussing about the slope stability, which is obviously the most important consideration whenever we are applying or we are considering in the geological considerations, as well as we are applying our engineering ideas or engineering in applications to build an infrastructure project. Any kind of infrastructure, be it a small house, be it a large dam or tunnel, you have to consider the slope stability that are present, or you have to consider the stability of the slope that are surrounding that region. Also you have to consider about the kind of foundation material that you can find on which the rest of your structure will be built upon. So the first kind of large scale infrastructure project is obviously the dams that we have been seeing for quite a time now. So your dams are obviously important for irrigation purposes. Also now mostly dams are also used for hydroelectric power generation. So dams could be of various types depending on the size, depending on the channel width, depending on the turbulence of the river and other considerations as well. And likewise they can be used the dam has a significant role to play in both in generation of your hydroelectric power as well as for irrigation purposes. So the types of dams are your arc dam, gravity dam, arc gravity dam, and then barrages, embankment dams, coffered dam, concrete face, rock fill dams, earth fill dams, like this. So there are various kinds of dams. I am not going to the individual properties, but if I look at some of them, then these are, for example, some embankment dam which are mainly prepared to restrict an event of flood, or to restrict water, or to store water for further irrigation purposes. Then you can think of the buttress dam. Here you have a dam with this kind of water storage, and these kind of dams are also mainly used for irrigation purpose. Sometimes they are also means they play a significant role in controlling an event of flood. Then you have these gravity dams like this, and also arch dam. These dams are more of, these are, you can say, these dams are used for hydroelectric power generation. So in case of a gravity dam, you have this front of the dam, that is towards the downstream side of the river will be the hill, and this will be the toe, that is towards the upstream side of the dam. Then you have the crest, and you have a large you can say bottom or trough of this dam, which is, that's why it is referred to as the gravity dam, which have a vertical upstream side and an inclined downstream side, like this. In case of arch dam, these are arcuate kind of or curved kind of dams. Again it is convex towards the upstream side and concave towards the downstream side. So this kind of dams are generally used for generation of hydroelectric power. So obviously there are several considerations for the construction of dams. The first one is obviously the economic feasibility, whether it is possible to build a dam, because it involves large cost, labor and materials. Then bedding planes and strength, like I was also referring to the different kinds of or different scenarios of slope stabilities based on the orientation of the bed, mainly the strike and dip direction of the bed. So your bedding planes and strength of the surrounding materials where you are building or you want to build a dam is obviously a very important consideration. Then again your feasibility and constructability, that how large a dam will be or how small a dam will be, it depends on the feasibility where you are or where you want to build that dam, and obviously durability and resistance to erosion. So preparing or constructing a dam in extremely highly turbulent water in a hilly region is obviously a problem. Nowadays also there are ways to support this kind of turbulence as well, but it is always a little bit problematic. but towards, you can say, when your turbulence of the rivers drops down a little bit. I am not saying it is going into the mature stage, but still in the youth stage also the turbulence is little bit low. In those areas you can prepare a dam relatively easily. And obviously there has to be measures to prevent erosion, because for dam you are actually storing water, so there will be erosional activities related to the streams and rivers. So these are also your various considerations for preparation of or construction of a dam like this one. And stability and saturation line and downstream phase are also important. I will simply discuss this one. Obviously stability, it depends on several other things as well, but saturation line where water meets the dam should be on the downstream face. The proper drainage and seepage control prevent internal erosion and maintain stability. So this is again a very important consideration whenever you are constructing a dam. So now if I look at this diagram again in relation to the orientation of the bed. So if you have a scenario where you have this W and T is nothing but the thrust force of the water reservoir, because you are storing large amount of water. So there will be always a thrust on the walls of the dam, so that is considered as your thrust force. And you have also your weight force, weight of the dam itself. It's a large scale structure, so it will impose a large weight on the surface itself. So based on these two components, again if I simply make out the, you can say, resultant vector, that is referred to as R here, or as the resultant force of the dam, then if the resultant force or the angle of the resultant force is at high angle with respect to the beds on which it is made, in that case it is relatively more stable with respect to the other cases. So in case, and this is possibly the most stable configuration, when your resultant direction of the force acted by this thrust force as well as simply by the weight of the dam, the resultant is at high angle or even orthogonal to the deep of the beds. So whatever water leakage will happen on the upstream side. So it will not affect the dam itself and the downstream side. So whatever water leakage can happen will only happen in the upstream side. Then you have this kind of an orientation, again the resultant thrust, the resultant direction of the force is at low angle with respect to the horizontal beds that are present. So your horizontal beds here though it is also quite stable, but still there is some possibility of some leakage in the upper layers of this horizontal strata. But these two, C and D, these kind of dams pose more of a problem, because here you have these vertical beds like this. So your water from the water reservoir can easily infiltrate through this kind of beds, leading to huge amount of water leakage. And in this case, this is you can say the most unstable kind of a dam configuration, where the resultant direction is almost parallel or subparallel to the deep of the deep direction of the bed. So there will be continuous water leakage along beneath the dam as well as on the downstream zone. So there is a problem that if this kind of structure you are getting, that these are dipping in this direction, you shouldn't construct a dam over here, because that dam will not be at all stable in nature. Now if I look at this particular scenario, where you can see that this is the dam, you have a spillway through which your extra water can be removed from the water reservoir, and this is your dead storage. So dead storage actually refers to your minimum pool level, and beneath this dead storage your water can't go. So your dead storage is actually related to the stability of the dam. So beneath that your water can't leak. So that's your dead storage, that is the surface or the minimum pool level. And you also have the maximum pool level that is beyond the normal one, or that is considered within the surcharge storage zone. So, this is the normal pool level till which your water or the dam can support the water reservoir, and whatever extra water is getting stored can be diverted through these spillways. But if in an event of a cloud burst or in an event of a torrential rainfall, if this normal pool level get or exceeds the water level exceeds the normal pool level and even beyond the surcharge zone or surcharge storage zone, then finally there will be a destruction of that dam. So, then this water pressure will be so much that the dam will not be able to withstand that, resulting into the complete destruction of that dam. So, you can see that how your geologic formation, their orientation are having a serious effect on the stability of a dam. So, just to mention here, the biggest dam in India is the Bhakranangal Dam in the Himachal Pradesh state. The longest dam in India is the Hirakund Dam in Orissa, and the highest dam in India is the Tihri Dam in the Garhwal Himalaya, that is in Uttarakhand. Now, coming to tunnels, because tunnels are again being made very frequently nowadays in India for both your roadways as well as for rail tracks. So, a tunnel is an underground passageway that is excavated through soil, rock or both. Tunnels are used for transportation, water conveyance, sewage and utility controls as well. They have a long history of use dating back to ancient civilization and have become increasingly important, like I was saying. Now tunnels are being frequently made specifically in India as well, and they are important in modern society for transportation and large scale infrastructure development. So, this is a view of a tunnel in Norway. Now, there are again several types of tunnels. Transportation tunnels, simply you can say that if you need to transport vehicle, rail or something else, you can transport through them. Utility tunnels, these tunnels are used to carry pipes, cables and other utility services like water, gas or electricity, sometimes telecommunication as well. Mining tunnels, these are constructed in mining operations for extraction of minerals and ores. Hydroelectric power tunnels, these tunnels are used to convey water to hydroelectric power plants, which are again related to your dams. Then sewage tunnels, these tunnels are used to transport sewage from one location to another, usually from a treatment plant to a discharge point. The type of tunnel chosen for a specific project will depend on its intended purpose as well as the geological and environmental conditions available for the construction of that tunnel. So, again for tunnel like dam, you need to have or you have to carry out site investigation and other geological consideration, and there are various methods also for these things that involves starting from deck study, means existing literature, geological maps, geophysical surveys, boreholes and also the strength means different kinds of strength measurements. Then you can directly look into the rock layers, measure the orientation of the different formations through which you are supposed to drill or make a tunnel. Then geological factors that might affect tunnel construction are rock or soil type, rock mass quality, geological structure, and again groundwater also plays a important role. Also, apart from that, large scale seismic activities, slope instabilities and also stability and environmental considerations are also important before proposing the construction of a tunnel. So, the orientation of rock or soil beds relative to a tunnel is extremely important. We will be looking at this example now. So, if you again tunnels and their stability, if I want to judge with respect to the geological considerations that I should consider before proposing or planning the construction of a tunnel, then the first one, stable tunnel with horizontal beds with uniform pressure from all sides. So, it is kind of hydrostatic pressure, uniform pressure from all sides. So, there will be a stability that will be maintained if you are only penetrating one thick layer of the horizontal bed. It becomes unstable if it is present within the dipping beds. Like across a few beds your tunnels are going, so it becomes unstable within dipping beds. Orientation of the tunnel parallel to the strike of beds, that is oblique pressure is getting applied here like this. So you have on one side of the tunnel you have a larger pressure in response to the other side. Tunnel length perpendicular to the strike of the dipping beds also pose some problems, because on some parts of the tunnel there will be oblique pressure. Tunnel across vertical beds with the top arch are again generally stable in nature, because this arch will support this vertical stress, like we discussed about the support offered by the non-rotational compression in the arch system in the Roman civilization, or the structures that were prepared during the Roman time. So again this one E and F, tunnel parallel to the fold axis in a folded bed. In case of an antiform obviously it will be more stable, but in case of synform also it is stable a little bit less, because there are obviously some pressure on the two sides or two walls of the tunnel, so it will impose some pressure. But mostly these tunnels are stable because they are restricted mostly in the hinge zone of a large scale fold, and they are almost running within a particular geologic horizon. And the G and H, this tunnel perpendicular to the fold axis, these are also not very favorable conditions, but still tunnels are being made today, because sometimes they are relatively, some sites are better than, though that is also not a very good site, but it is relatively better than the other. In that case we can also choose this kind of tunnel that are constructed perpendicular to the fold axis, and in this case it will have again oblique pressure of different layers on different parts of the tunnel. So at certain zones the oblique pressure will be more, at certain zones the oblique pressure will be less. So there is a differential pressure throughout the tunnel that might also lead to some problems, or means you can say the problems in resisting the instabilities offered by this oblique pressure. The longest tunnel in India is the Chenani Nasri tunnel, also known as the Samaprasad Mukherjee tunnel, with a length of 9.28 kilometers in the state of Jammu and Kashmir. Then finally we will be now looking into the engineering consideration for construction of bridges. So a bridge is a construction designed to span a physical obstacle such as river, valley, road or railway without obstructing the passage underneath. Essentially, bridges provide a way to cross something that would otherwise be difficult or impossible to traverse. So there are again various kinds of bridges: beam bridge, truss bridge like this, then you have this arch bridge like this, suspension bridge like that of the bridge in the city of San Francisco, USA. Then cantilever bridge, remember if you have seen a photograph or physically you have seen the Howrah Bridge was at some point of time in our history. Howrah Bridge was the largest cantilever bridge in the world, but now after the construction of several other cantilever bridges, now it ranks third among all the largest cantilever bridges across the globe. So now, apart from that, you have cable stayed bridges like the Sea Link bridge in the city of Mumbai, that simply traverse the Arabian Ocean to join some the parts of Bandra to the further northern part of Bandra. So that's your again cable stayed bridge in that we can see in Mumbai in India as well. Tied arc bridge, this is again an example of you can think of the famous bridge of Sydney just near the Opera House, where you will get this kind of tied arc bridge like this. But again for bridges as well, again you have to go on in the same manner. You have to select the site, you have to design the foundation, you have to look for the foundation material, you have to look for the feasibility. Also, in case of bridges, whenever we are, for example, constructing a bridge across a river, you have to also always try to get the narrowest channel width. But if at some place there is no other option, then you have to look for obviously reliable foundation material with little or no instability on the two sides where the main, you can say, the pillars are present to support that bridge. So, the geological considerations include the subsurface conditions, faults and shear zones, seismic activities. Other geological hazard assessment are necessary, like there is a probability of landslide or not, whether there is a formation of sinkhole or not, like we discussed in groundwater, and other factors, water factors like groundwater levels and scouring of materials. So, construction material selection, like I was mentioning, and bridge design are also extremely necessary before thinking of constructing a bridge. So, again, based on the types of foundation rocks and stability of bridges, again I will look at the first one. Stable bridge on uniform foundation rock type. The foundation rock type is not changing much, it is uniformly bedded, and the rock type is, for example, it is granite gneiss, so there is no change in the rock type, and you can put two abutments at the two end, and you can support your bridge with the help of pillars and also across the overburden that is present. So, if you are constructing a pillar on the overburden, there is high probability that with time that overburden can also get eroded very easily, and your bridge, again the pillar as well as the bridge, will become instable or unstable over the time. So, that is why you have to penetrate the pillars or piers through your overburden. Then in the second case, unstable bridge on composite foundation rock type like this, if there is a fault or there is a shear zone, obviously that impose a threat to the foundation of the bridge. It will be risky to construct any bridge in this kind of a large scale fault or shear zone, because these faults can get reactivated again and again, and if there is an abutment that you have kept near the fault or on the for example hanging wall of the fault, there is high probability that in an event of reactivation, that abutment can go means that abutment can be destroyed or might get destroyed due to the movement induced by the fault. So, this kind of a scenario is again not a suitable one for constructing a bridge, as well as you can see there is changes, continuous changes in the rock type, starting from kind of igneous rock, granites here, and some sedimentary rocks that are present here. And again in the third one, where your bridge again becomes unstable because of the sloping beds here, and you are keeping your abutments of the bridge on the sloping surfaces. So, again this is not a favorable site for the construction of this kind of a bridge, and you can look at the structure of a normal bridge with these pillars and abutments on the two sides of a river channel. For example, just to mention one Indian example, the Dr. Bhupen Hazarika Setu, or the Dhola Sadia bridge across the Lohit river connecting Assam and Arunachal Pradesh, is one of the modern bridges we have in India, and it is having a length of around 9.15 kilometers. So, with this I would like to end my discussion on the geological considerations for the preparation or construction of dams, tunnels and bridges. Thank you.